In this lesson, we are going to look at what does the graph of a square root function look like. So in order to work with a square root function, we must first understand what squaring means. So 6 squared, that means 6 times itself. It's repeated multiplication. So 6 times 6 is going to be 36. Negative 6 squared is negative 6 times negative 6, and a negative times a negative is positive 36. Be sure when you're using a calculator, if you punch in negative 6 squared, you need to include parentheses around that negative 6 before you square it. How about 1/6 squared? Well, that's just 1/6 times 1/6. So 1 times 1 is 1, 6 times 6 is 6, so that gives us 1/36. You try the next ones on your own. So let's check your work. What values are the result of squaring a number? We're going to select all that apply. So answer choice A is 12. There is no number times itself that will equal 12. 16, it is a perfect square, meaning when we take the square root of it, we equal 4. Because 4 times 4 equals 16, we will select that as one of our answer choices. 26 is not going to be selected here because, again, there's no number times itself that will equal 26. 50, there is no number that you multiply times itself that equals 50. And then finally 64, we can take the square root of 64, and that equals an 8. So that means we will select this one as a value that is a value of result of squaring a number, because 8 squared is 64. Let's look at the square root of a negative number. The square root of a negative number is not defined in the set of real numbers. So for example, the square root of negative 64, the result is actually an imaginary number. So it's an I, looks like a backwards J, but that is an I, a notation we use in math for imaginary numbers. And yes, there is such a thing. So there is no number when multiplied by itself that will equal a negative number. We can't even use negative 8, because negative 8 times negative 8, that will equal positive 64. So do not get confused and think that the square root of negative 64 even equals negative 8. That is not true. So let's begin now by looking at the graphs of a square root function. The parent function, f of x equals the square root of x, parent function. So that's just the most basic function of a square root function. So here for our graph, we are going to select some x values in our table that we can take the square root of. So let's start with 0. We would not choose anything less than 0 because that would be a negative number, and like we just talked about, we cannot take the square root of a negative. It's not a real number. We couldn't graph it on this real quadrant plane. So f of 0, let's plug that in. We take the square root of 0, and that gives us a 0. So our output would be 0 when we have an input of 0. Let's choose another number, 1. So f of 1, let's substitute that into our function. When you take the square root of 1, you equal 1, because it is a perfect square. 1 times 1 equals 1. So our output would be 1 there. Let's keep going, trying 2. So f of 2, when you take the square root of a 2, it actually gives you a decimal. So let's see that in a calculator. So square root is the second square root key. of course have it turned on, second square root of 2 gives us a decimal 1.41. So we may not really need to graph that point, but it is good to have it as part of our table just so we can observe that when we get to our graph if it approximately passes through there. So let's move on and pick other values that will work nicely for our table. So we're actually going to skip over 3 and try 4 because 4 is a perfect square. So f of 4, when we take the square root of 4, it does give us a 2. So we have that as our output value when our input is 4. So let's plot these points. 0, 0 at the origin, 1, 1, so to the right 1 and up 1. We'll wait on that 2 and 1.41. We'll come back and talk about that one. But let's do 4, 2. So over 4, up 2. We will connect them with a smooth curved line, and that is our parent function. That is the graph of a square root function. So let's talk about a few things here. First of all, we will notice here, so if you want to grab a highlighter, right here at this end of the graph, there is no arrow. No arrow on that end. Because the graph does not extend past that point 0, 0. Because again, if we plugged in a -1, that would result in an imaginary number. And so we would not graph anything beyond that beginning point of 0, 0. So no arrow even on that end, because that arrow shows that it continues, and that is not the case there. Let's look at this point 2 that we talked about. Here we have, if we went over 2 and went up 1.4, almost 1.5, well, look where our graph is. That is approximately there at 2 and 1.4. So there are points all along that graph. Let's talk about some domain and range. So again, I'm going to highlight here. For domain, we're going to talk about our x values. So along the x-axis, what x values is your graph touching? Well, look, it starts at 0 and goes on out and forever to infinity. So that is a positive infinity out in that direction. So for our domain, we're going to say the set of all x's such that x is, we're going to choose all the numbers that are greater than or equal to 0. Because 0 is our starting point, all of our x's got greater than or equal to that 0 value. Let's look now at our range. So again, I'm going to use a different highlighter. Here for our range, we're talking about our y-axis. So imagine which y values is your graph going to reach. Okay. We never drop below down here in the negatives. We stay here at 0 and always go greater than that. So for our range, we're going to have the set of all y's such that y, it turned greater than or equal to that 0. They never drop below the x-axis in the negative values. So now you try the next one on your own. Let's check your work. Which points are on the graph f of x, the square root of x? That's our parent function. We'll select all that apply. So for our first one, if we had the input of a -4, so f of -4, when you plug that in, that does not result in a 2, so we cannot select that one as an answer choice. For the next one, if we do f of 100, so taking the square root of 100, that is a perfect square and it does result in our output of 10 there, so we would select that one. part C, f of 25. So if I plug in 25, the square root of 25 does equal 5, but it doesn't equal the square root of 5. If we had an input of 25, once you take the square root of that 25, it uses that symbol. So we no longer would keep it around the 5. Now if that said 25 and 5, we would have selected it. But because it's the square root of 5, we would not select that one here. For part D, if we had our input value of -16, remember taking the square root of a negative results in an imaginary number, so we will not pick this one because it shows an output of -4. So that would be incorrect. F of 10, when we take the square root of 10, because 10 is not a perfect square, we would not be able to take the square root of it, so we would not select that one either. And then finally, f of 121. 121 is a perfect square and it does equal 11, so that would work for this function. Let's now look at reflections of square root functions. So we're going to have the function g of x, and notice we have a negative on the inside of our radical. So a negative inside the radical, we can work with that. We just have to be careful what input values we find in order to evaluate this function. So let's first start with 0. So g of 0, we can substitute in, well, -0 is just really 0. So when you take the square root of 0, our output is still 0, so no change there. If we do an input of 1, so g of 1, well, once you substitute in that 1, you cannot take the square root of it. So inputting a +1 would keep us from being able to do anything with this function. So let's change that to a -1. So g of -1, well, when you take, that's a -1 times -1, that's what that is in front of the x, that's a -1. So negative times negative is a positive, and the square root of 1, we can do that, that is a 1. So the square root of 1 is 1, that gives us an output value. So what you're going to do is, our inputs that we're going to put in, you're going to make them the opposite so you can take the square root. So let's choose our next one wisely. Let's go ahead and just do -4. Since we know 4 is a perfect square, once we do the opposite of that, we're going to be able to take the square root. So g of -4, so we want a -1 times -4. Negative times negative gives us a positive, and that makes it to where we can take the square root. So square root of 4 gives us an output of 2. Let's choose one more value. I'm going to choose a -3. I know it's not a perfect square, but that way we can still see where does that fall on our graph. So as an input value, g of -3, we have the square root. We'll take -1 times that -3, which gives us a +3, and we'll use a calculator to find that value. The square root of 3 gives us approximately 1.7. Was 1.73. So that is our output value. So we'll plot these points and then just kind of check that -3, 1.73. So 0, 0. And first of all, on our graph, we already have the parent function. So that's our f of x function. We're in graph now g of x. So we have 0, 0 at the origin, -1, 1, -4, 2. We're going to connect those with a smooth curved line. Now this -3, 1.73, if you go over -3 and go up 1 and 0.73, not quite to 2, but it's reaching there, so that does make sense for -3 and 1.73. It's right there on our graph. So this is the graph of g of x. So notice what's happened. When we have the negative on the inside with our variable x, meaning we're taking the opposites of our x's, that's exactly what happened to our function. Took the opposite of our x's. So that's a reflection across the y-axis. We can write this in function notation as our function g of x equals the function f, and then we changed all of our x's to be opposite of what they originally were in the function notation. So g of x is our function, our parent function f, where we take the opposite of our x values. So this is a reflection across the y-axis. Let's talk about the domain of this function g of x. So for our domain, we're going to look at which x values our graph will reach. So here along our x-axis, it starts out at 0, but this time it turns off in the negative direction. So our domain, we'll say, is the set of all x's such that x's, this time they're going to be less than or equal to, and since they started right there at 0. So the domain of this square root function, when it's a reflection across the y-axis, is the set of all x's such that x is less than or equal to 0. Now for our range, let's look at the y values this graph is reaching. So along our y-axis, we see that our y-axis, it touches all of these that are in the positive direction, starting at 0 and increasing in that positive direction. So we have the set of all y's such that y, this time it's going to be greater than that 0. So notice our range in this case, when we had the reflection across the y-axis, ends up being the same as the parent function, but our domain is different. Now let's look at a reflection across the x-axis. So notice our function. We now have h of x with the negative on the outside of our radical, where we're taking the square root of x. So here we have our x values that we're going to substitute in. So h of 0, negative square root of 0. Well, that's just negative 0 once you take the square root. Well, 0 is neither negative or positive, so it's just 0. Let's do h of 1. So negative square root of 1. The square root of 1, as we know, is 1. And then we get an output of a negative 1, because once you take the square root of 1, that negative comes over with it, so we have an output of negative 1. H of 4, so negative square root of 4. Well, the square root of 4 is 2, so we have negative 2 as our output. And then finally, h of 9. We have negative square root of 9, so that results in a negative 3. So let's plot these points. We have 0, 0. Again, this is our f of x function that's already graphed. For our h of x function, we'll start at 0, 0. We have 1, negative 1, so to the right 1 and down 1. 4, negative 2. And really, that's enough points to make our square root function. 9 and negative 3 actually doesn't even fit, but you can imagine it being out there, out to the right 9 and down 3. So connect your points here. Smooth curved line. There it goes. So that is the function h of x. So notice what happened there when we had the negative on the outside. That resulted in a reflection across the x-axis. We're taking our parent function and making everything opposite as the output. So everything, as we did our inputs, our outputs were opposite of the parent function. So it reflects that across the x-axis. The function notation for this type of reflection, we are going to have that our function h of x is going to equal the opposite of our parent notation, f of x. So h of x is going to equal the negative of f of x. So that's our function notation for this type of reflection. Let's look at the domain of our h of x function. So for our domain, we're going to, for our domain, we'll look at that first. Our domain are going to be our x values. So along our x-axis, what values does our function reach? So starting at 0, and it turns off there in the positive directions for our x values. So we have the set of all x's such that x is greater than or equal to 0. Now let's look at the range, the y values of this function. So our y-axis, the values that this graph is going to reach, starts at 0, and because they were the opposite of our parent function, instead of turning up in the positive direction, they all turn down here in this negative direction. So they start at 0 and go less than. So the set of all y's such that y is less than or equal to 0. You try the next problem on your own. Let's check your answer here. So which is the graph of p of x, which is the negative square root of negative x? So first of all, notice the first answer choice is the parent function. This is just the plain f of x function, so that definitely does not match p of x. So when we're looking at p of x, we got to ask ourselves, what does this negative out front do? The negative out front goes as a reflection across the x-axis. The negative on the inside causes a reflection across the y-axis. So we're going to be looking at our parent function and seeing a graph that goes a reflection across the x-axis and a reflection across the y-axis. So the only graph that does that, we can see the second choice does a reflection across the y-axis, but then we need to also reflect it down into the next quadrant to make it a reflection across the x-axis also. The only graph that does that is this third one here. That would be our function p of x. Now let's look at vertical and horizontal translations of the square root function. So the equation of a vertical translation of a square root function has the form g of x equals the square root of x plus k, or that plus k is on the outside of the radical. So if k is a positive number, then the graph of the parent function is going to translate up k units. If k is a negative, then the graph of the parent function is going to translate down k units. Let's go ahead and look at horizontal translations. Those will be of the notation g of x equals x, the square root of x minus h, where that is on the inside of the radical. So if h is a positive number, then our graph is going to translate h units to the right, and if it is a negative number, then our graph is going to translate h units to the left. So let's look at some of those examples. Here we have a list of functions, and we're asked to describe the transformation to the parent function, which is given there, just the f of x, the square root of x, for each of the following. So let's first look at g of x. In this function, we have a k value. When you're finding the k value, you're going to write down the exact value you see. So if you see a positive 3, you're going to write down that exact value of 3. So that means the transformation that occurs is up 3, or up 3 units. In our next function, h of x equals the square root of x minus 3, this time we have an h value. When you're naming your h value, you're going to write down the opposite of what you see. Because of the transformation form, it's supposed to be x minus h under that square root symbol. So because you see a minus sign, you're actually going to write down the opposite of positive 5. When that h is a positive, it causes the graph to shift to the right. So we're going to see this go right 5. Let's look at our next one. Here we have an h value. Again, remembering to write down the opposite of what we see. So we see a positive 9, we're going to write negative 9 as our h value. Always remind yourself, opposite for h. So because that is a negative, we will see the graph move to the left 9 units. Looking at our final example here, j of x equals the square root of x minus 2. Here we have a k value. When you're naming the k, you write down the exact value that you see. So if you see a negative 2 on the outside of that radical as your k value, that's what you write, negative 2. So a k value being negative makes the graph go down that many units, so down 2. You try the next one on your own. Let's match these functions to how the graph is related to the graph of the parent function. So first, I like to look at the ones that go up and down because I don't have to think about any opposites when I'm thinking about my h and k. When it's a k value, you can think exactly what you see. Plus 7 will make it go up, so an A function, the answer choice A matches with that k function, and the minus 7 makes it shift down. So those I have matched up. Now with the g of x function, we have to think about when we see that plus 7, that actually means that our h value is negative. So that's going to be a left or right movement. Because it is negative, it is going to go to the left. So that is answer choice C. So that means here for the last one, we have an h value of a positive 7. So again, writing down the opposite of what you see. So if it's a positive 7, it's going to go to the right 7. Now let's put those translations of the cube root, or this is a square root. Translation of those square root functions all together. The equation of a horizontal and vertical translation of the square root function has the form f of x is the square root of x minus h on the inside and then your plus k on the outside. So we can see these functions having the translations together at the same time. We have our graph here provided. It's asking us how does it compare to the parent function. So you can use your graph to help you explain, or use your function naming your h and k. So we'll look at both. Here in our function, our h is going to be a negative 2, writing down the opposite. And our k is going to be a positive 1, writing down the exact value. So looking at our graph, if we evaluate here at the origin 0, 0, and compare that with the starting place of the g of x function, it moves left 2 and up 1, which is exactly what these h and k values would tell us. So g of x is shifted left 2, and up 1. To write the function notation for this g of x function, we can say that g of x is going to be the main parent function f of x, where we had to add 2 to our x values, and then plus 1 on the outside of the function to cause that vertical translation. So f of x plus 2 on the inside, and then the plus 1 on the outside to represent those transformations. Now you try the next one on your own. Let's check your answer. Which equation is graphed with the parent function? So here's our parent function, the dashed square root function. So that's f of x. We're going to try and match up our answer choices to this graph here. So we go left 1 and down 3. I can start with narrowing out my options with the down 3. That's easy to see because we don't have to think about any opposite values. We see the -3, which results in going down 3. So now to go left 1, we would need to have an h value of a -1, but don't pick the -1 on the inside because remember it's got to be opposite. We're actually going to pick the +1 on the inside. So answer choice D has a h that is -1 and a k that is -3 that results in that left 1 and down 3.